Okay. So, my name is Nino Vidovic. I work at Zegger as a software engineer. And as a continuation of my debugging talks, I will now talk about real-time transfer, RTT, the better printf, and more. So, my talk content will look like this. I will have an explanation on the standard printf, which most of you are probably familiar with. I will show you what RTT is, what the technical background of this will be, what example use cases can be for such a technology, and we will have a conclusion and an example that I've prepared here, so you know that it's actually running on hardware. So, first, let's take a look at our standard printf that we are all familiar with. It's short for printf, for print formatted. We put a string in it, and it's for a formatted string. We have some I/O handling, and then it appears on our host system in some kind of debug terminal. Typical channels here are UART, or if you're on ARM, it's usually semi-hosting or SVO. And the biggest problem of printf usually is if you use it, it slows down your system. You waste cycles, but mostly because of these I/O channels you implement. And this is something you want to try to avoid on embedded targets where you have limited resources and you have to make the best of each CPU cycle. And this is something where, at least I think, RTT can be a big helper. So what is real-time transfer? It's essentially a little buffer block in your RAM. We have an up and down buffer, so we have both directions implemented. And the nice thing is we have a minimum impact because we only need to do a mem copy essentially to your RAM, and we leave the data there for now. And everything else is handled by a debug probe. In this case, you will need at least a J-link. But as I talked to a couple of you guys, you already have some, so this is free technology. You can simply use it on top of the debug probe you already have. This works while the target is running on ARM Cortex and RX devices on RISC-V, so this is something new and exciting. So if you're looking into RISC-V, this also works here on most implementations, and it's implementation defined on Cortex-A and R targets. The great thing is we don't need any additional hardware pins that we usually would need for hardware tracing, but we just use the debug interface, so be it JTAG or SVD, so no extra pins, it's just a standard debug interface. So let's come to the technical background here. So we have some kind of up and down buffers. We have three operating modes. We have skip, block, trim. Skip would be that you have buffer. If it's full, you throw away the new data. Block would be that when the buffer is full, we halt the application. And trim would be if you have some buffer space left, we trim the new incoming data, and the trimmed data is thrown away. And then it behaves like skip. The typical memory footprint of this for the printf implementation would be about 500 bytes in ROM, and per up and down channel that you implement, it's 24 bytes for the general control blocks. So we find the control blocks with our software and the size of buffer plus a little bit in bytes. So it's very, very tiny. Very tiny and simple implementation. And just to get some comparison to the other implementations I talked about earlier, when we talk about the transfer speed, so how much data can I transfer between my host system and my target per second, it's with the example setup explained here, it's around 2,200 kilobytes, which is, I think, quite a lot if you're looking to do just logging or some other nice things that I will talk about later. So, and then we have a little benchmark comparison here, which is the time to output 82 characters. And as we see, compared to SVO or semi-hosting, RTT is miles away, and we have microseconds here, so this is very, very fast. And if you're looking to use, even in production code, some kind of I/O implementation for, say, some later maintenance mode, this is something you can use without really impacting your real-time behavior on your target. All right, what are example use cases? So you can of course do I/O operations, so you can either grab data from, extract data from your target, or you can also use this as an input device if you want to test things with an user input or want to change variables while debugging. You can also do it in that direction. So, as I said, data logging, but also because of this high data rate that we have and the low impact on your system, you can do code instrumentation or software tracing with this, which our software system view, for example, is based on, which I can also show you in demos outside if you're interested. Here on the left, you'll see free software from us. It's the JD RTT viewer, which you simply get with our software package, where you can which is simply our terminal application on your host target. And you can also see that we support colored printf, so you can also do some stuff like warning messages and stuff like that during your runtime without impacting your system greatly. And on the right is a little picture showing how system view looks like, where you can check your real-time behavior of your system, task switches, and stuff like that, and do more deep analysis of your system. And as I said, without really impacting your real-time behavior here. So, what's the conclusion that we take from all this? So, I think RTT takes the whole printf idea to a complete other level. We don't have all this overhead anymore. We can simply use this, don't think about it, and still have our near real-time behavior of our system. As we saw, it's magnitudes faster than what most people are using currently. And yeah, because of this little low memory footprint, the fast integration, and the very, very simple usage, it's a perfect fit for any setup which considers using at least printf or some more advanced debugging techniques like, say, software tracing. And I will next demonstrate how this looks like on hardware when you are using the RTT viewer, for example. I will just use my example setup that I have set up outside. So it's the JTrace Pro and some STM32F4 or 7 target device board. But as I mentioned earlier, it would work on any of these architecture types and core types that I listed. So let's get into the live demonstration. So first we have, I'll show you how the implementation or how the source looks like. It's usually, you can usually find it when you install our software package. You go to the install folder, and then in the examples folder there you will find the RTT sources. Usually it's just 4 files that you need to implement this I/O terminal. I will open a sample now in our IDE so you can have a quick look how this might look like. So let me move this over. All right. Oh, maybe it's better when smaller. Do you see this? Yeah. It's a little small. Better.
Size is really small.
I see. Microsoft Zoom. Yeah, I would have to do some option changes. I can show you in a better resolution outside if you're interested. I will just so you get an idea what you need to implement on your side. So it's just these 4 files. That's all I wanted to show. So it's a C file, 2 header files for configurations of your up and down buffers, and you can also we have also prepared for you syscalls files which replace the printf call for the standard implementation of most IDEs out there. So you don't have to think about, oh, how did they implement it in their standard library. we have it prepared for you, so you just have to use it. So I will just flash the application, and then we can see inside the debug terminal here how fast it actually is. The application is simply a hello world loop. It does currently nothing but print, but I want to show here that we don't have any overflows or whatever, and it doesn't slow our system down. So I just run it, and you see it's pretty quick, and we don't drop any informations. And this is currently with the default configuration where the up buffer is just 1 kilobyte in size. And I will now show you the Rtt Software Terminal, which again is working standalone, so you don't have to have some IDE or whatever running. Let me move this over here. So this is how it looks like. We go to connect to it. Here you select your connection type. This would also work over telnet, so our probes also open a telnet port, so you can remote into this terminal also with PuTTY or stuff like that. So if you don't like our tools, use whatever you like. You select the target device. The interface speed, I will leave it default is usually for our tools 4 megahertz. You can go lower, you can go higher. Of course, the higher you go, the more data you can transfer, but you will see that 4 megahertz are completely enough for the setup. And I just press OK, and again, we see our data stream coming in without any hiccups or anything. So yeah, great technology, and I would like to see more people using it, especially if you already have such a probe. So it's free, it makes your system better, and yeah, let's take printf to another level. Thank you. Yeah, questions? Yes? Do we have a microphone, or? Yeah, it's coming. Currently not. It's J-Link exclusive, and we even have it patented, so even other companies couldn't really implement it without our allowance, essentially. Yeah.
Does your printf also work with the release build?
Yes, sure. As I said, this is also something that a lot of customers consider using in some kind of maintenance mode. Say you have your software running in some closed-up system, and now you need to extract this data, and then you go to the debug terminal, and then just switch to this maintenance mode where they then start printing their logs or whatever. And yeah, this is something that you can definitely use in your release builds or production code, essentially, because it has such a low impact on your performance. Yeah.
So you mentioned that one could telnet into the application. Mm-hmm. Did you mean with that I need a running server software on some kind, and I telnet into your debugging program, or I can telnet directly to the probe?
To the probe. So the probe opens the port. It's usually a local host port is open, but you can also go remotely over the network if your computer or setup is somewhere else. Works also. Yeah.
Yeah. Hi. So these 500 bytes, they are for the printf implementation, I guess, for the formatting and everything. Can I use it without? Like, what would it take to just write the string without the formatting?
Well, you can of course link everything to RAM during boot, and then clear your flash if you need the extra ROM.
flash, and I don't have any lot of RAM space.
Yeah.
So
well,
basically, and I don't need printf. I just want to write the string, right?
If the thing is, we already have a pretty minimal implementation to create this buffer. If you can recreate this buffer somehow, because the probe is simply looking for this characteristical buffer topology in RAM. So if you can create this with less code, go ahead.
Okay.
This is just a helping tool if you use our source.
Okay.
It's a standardized API. You can simply go into it with our samples. But if you can recreate this buffer somehow and make it smaller in your code, it will also work.
I see. Yeah. I mean, I can just use your code and adapt it. Okay.
Yeah.
Thank you.
Okay. Then I think that was all. Okay. Thank you again. See you later.